All right, good afternoon, everyone. Welcome to the Australian Academy of Technological Sciences and Engineering, or ATSE. This is our head office in Canberra, and we're delighted to have this webinar and event today. We've got quite a few people joining online, expecting over 100, and you all in the audience today. So we'll have some great presentations and discussion. So feel free to bring any questions. We'll have plenty of time for discussion at the end of the presentations. Before we start today, I'd like to hand over to John Dixon. He's the chair of the ACT division of ATSE here in Canberra, and he'll do our acknowledgement of country and welcome our speakers today. For everybody who's joining online, I said it at the beginning, but if you put your questions into the Q&A facility, we'll be moderating your questions and directing them to our speakers during the discussion component of the event. Thanks very much. Over to you, John.
Thank you, Edwin, very much. And let me extend the welcome to everybody, and let us kick off with acknowledgement of country and acknowledgement of the traditional custodians of the lands on which we meet around Australia and beyond. And in our case here in Canberra, the Ngunnawal, and pay respects to the elders past, present and emerging, and also pass and keep in mind the knowledge base from 60,000 years of occupation and management of the environment within Australia. So it's my very great pleasure now to introduce two exceptional speakers that we have for this webinar on debunking myths around renewable energy. In this era of misinformation and lack of information in many quarters, as technology and society and economies move ahead more and more and faster, we would appear to have a lot of key actors, as well as the general population, who are not fully up to speed with these opportunities from science and technology. And so it's in that context that debunking major myths becomes so important. So our two speakers, first of all, Professor Kylie Catchpole, who is Deputy Director of the School of Engineering at the Australian National University. Kylie is very well known in Australia and internationally for her work on solar cells and on solar hydrogen generation. And these are two areas that are very much in the news in Australia and beyond. Kylie is also the recipient of the John Booker Medal for Engineering Sciences within Australia, awarded by our sister academy, the Academy of Science. Our second speaker, who will follow straight on from Kylie, will be Professor Ken Baldwin. Ken's also very well known in Australia and in the near region and beyond. And he was the inaugural director of the Energy Change Institute at the Australian National University, which was recently rolled into the Institute for Climate, Energy and Disaster Solutions. Ken was also the founding director of the Grand Challenge program on on energy, zero carbon energy through not just Australia, but the region of Asia Pacific. So both of them bring exceptional understanding from the fields of renewable energy and its relationship to our capacities and to our policies. Please, as Edwin mentioned, through the course of the presentations, which will take about 20 minutes each, please do put all of your questions, if you're online, into the Q&A button at the bottom of your screens. and we will use that as the basis for the follow-up discussions, as well as questions from our audience in person here in Canberra in the ICEDS office. So please remember that we'll be moving through normally for at least 60 minutes. And at that moment, we can release people from the webinar for other commitments. But if you still have got key questions that you'd like to put to our speakers, we can roll forward for a few minutes more. So without further ado, it's my pleasure to pass to Professor Kylie Catchpole.
So thank you very much, John, for the introduction, and thank you, ICEDS, for the invitation. It's great to be here. So to start off with, it's good to get an idea of the situation that we're facing. And the International Energy Agency has put it very starkly in their report from 2021 that says the world has a viable pathway to building a global energy sector with net zero emissions in 2050, but it is narrow and requires an unprecedented transformation of how energy is produced, transported, and used globally. So this is the biggest change in how we use energy since the Industrial Revolution. We have to be aware of that. Further, they said that means from today, no investment in new fossil fuel supply projects. It means by 2035, no sales of new internal combustion engine passenger cars. And most relevantly for the talk today, by 2040, it means the global electricity sector has already reached net zero emissions. So that means in order to get net zero emissions by 2050, electricity has to get there by 2040. That's a very short time frame. The good news is that we're already in a transformation of how energy is being used. So what we're showing here is the annual net new capacity that's being installed per year by different technologies. So you can see on the left there is photovoltaics, solar photovoltaics, which is the largest energy technology that's being installed by capacity each year now by far. Second is wind, and then we have gas and coal and other technologies. So we're already at the beginning of a revolution in the type of energy that's being installed. Other organisations have come to the conclusion that wind and solar are the key technologies that we need for this transition. So this is a report from the IPCC, and it compares a range of different energy technologies, and it shows you their capacity to contribute to net zero emissions. And what you can see is that the capacity of wind and solar to contribute to net zero emissions are much larger than any other energy technology, and also that they're much cheaper. So the blue shows you where it's actually cheaper to go with wind and solar than with the standard fossil fuel options. The other important thing to note is just how important the contribution from wind and solar will be. So this shows you from the International Energy Agency Net Zero Roadmap for 2023. It shows you the red line of where we would be going in terms of emissions from the pre-Paris baseline. And you can see where we will be heading under the stated policies, which is the blue line at the bottom. And the bit in between, you can see how much of the contribution is going to come from wind and solar. So solar is projected to reduce emissions by 3 gigatons of carbon dioxide by 2030, which is approximately equal to the emissions from all the cars on the road today. So solar and wind are crucial. There's many other things that we need to do, but particularly we need to install this solar and wind if we're going to reduce emissions at the scale that we need to. So that brings me to our myths, and Ken and I are doing a bit of a double act today. So we have 4 myths that we'll address, and I'll address the first 2, and then I'll pass to Ken, who will address the second 2. So the 4 myths that we're going to address are firstly, that renewables can't meet demand and keep the grid stable 24/7. Secondly, that renewables take up too much land. Thirdly, that renewables are too expensive. And fourthly, that renewables can't replace our energy exports. So let's go to the first one. Renewables can't meet demand and keep the grid stable 24/7. To get an idea of what wind and solar can do, it's good to look at the history. So this shows you the history of installation of solar photovoltaics over the last 20 years or so in the terms of the global installed capacity in gigawatts. What you can see is that now we're installing around a terawatt. We've installed around a terawatt, and this compares to around 40 gigawatts in 2010. So that's a factor of 17 in 10 years, which is equivalent to a yearly growth rate of around 33%. That's an enormous growth rate for any industry to maintain over that timescale. Of course, we need to keep going. And so this shows you projections going into the future of what we would need to do if we wanted 50 to 70% of global electricity demand by 2050. So this is the scale of what we need to do. What we would need to do is to keep going at these growth rates. So we'd need 25% growth rate to continue to around about 2035, and then it can flatten off and just decrease to the replacement rate. If we're able to do that, then we can get most of electricity powered by solar by 2050. So this gives you an idea of what we need to do. We need to increase the annual installations globally from a third of a terawatt to 3 terawatts. But again, looking at the history of what we've done previously, this is certainly doable. We just need to keep going. So that's in terms of meeting the demand globally. The other thing that we need to think about is reliability. Now, when we think about reliability, you need to think about a range of things. People immediately jump to storage, but for renewables, you need to think about a range of things. So firstly, you need to think about sectors will be coupled now. Power, transportation, and heating will all be coupled together through electricity. So there's scope to think about when electric vehicles are charging, when you're using your heating. All of these things are part of reliability. You need to think about geographically where you place these things. And if you have your wind and solar in a variety of locations, that increases your reliability. There's technical diversity, so having a mixture of both wind and photovoltaics, because they tend to be anti-correlated and produce power at different times. And then you go to your storage technologies. So that's pumped hydro, electric car batteries, hydrogen, and other standalone batteries. So focusing now on Australia, we can look at how much we need to make this energy transition. And this shows you the Australian Electricity Market Operator Draft 2024 Integrated System Plan, which shows you what we'll need to do in order to transform to a high fraction of renewables in the grid. What you can see is firstly that we've already made a significant transition over the past 10, 15 years. We have a significant fraction of solar and wind in the grid now, which we didn't have before. The other thing you can see is that we will need a lot more rooftop solar, utility scale, onshore wind, and different types of storage in the system. So all of these need to grow significantly, and the capacity needs to grow significantly because we'll see increased electrification demand due to electric vehicles as well as electrification of heating. The other thing when you're thinking about storage is to be very clear on power versus energy. So this is a key point to understand. I'm just illustrating it here with an analogy about flow rates of water. You can see that on the left we have the cup. It's delivering a small quantity of energy with high power, whereas the jug can deliver a large quantity of energy, but with low power. And that just really helps you visualize the difference between power and energy. And both of these are important for storage on the grid. So when we're thinking about how much storage that we need to look at both power and energy. So these are also graphs from the AEMO 2024 Integrated System Plan, the draft version. And you can see that the picture is quite different whether you look at power versus energy. So we have on the left, you could see they've called it CER. That means consumer energy resources. So we're basically talking about home batteries and home electric vehicles. So those, and most of them are coordinated, which means that we will need to control how they're charging and discharging into the grid. And if we can do that, they'll provide strong support to the grid. If you look on the energy side, this is the right-hand side, the picture is very different. So this is how much energy capacity can be provided. And you see it's completely dominated by Snowy 2.0. So the batteries are providing power. So they're providing large amounts of power for short amounts of time. We're talking hours. Whereas the deep storage, Snowy 2.0 and other types of deep storage, such as Barumba, those are providing relatively smaller amounts of power, but for really long amounts of time. Just to show you a little bit more about Snowy 2.0. So this is going to give you energy balancing over periods of days. So it's expected to be able to provide energy for 175 hours of operation. So that's over a week. This is very different from batteries, which are providing hours. People are talking 2 hours, 4 hours, up to 8 hours, but we need this deep storage in the system as well. People sometimes say that there aren't enough geographical locations for pumped hydro, but there's been work done at ANU showing there's really thousands of sites around the world. So it's just a matter of where you want to put them, and that includes very many sites in Australia. So moving on to batteries now. So batteries have a different profile and they're good for lots of different things. Particularly batteries can respond very fast to disturbances. So they're good for short-term storage of the order of hours. They're good for helping with transmission constraints, and they're good for maintaining grid stability. So they're playing multiple roles in the grid. To give you an idea of one of the things that they can do, they can help with frequency control. So I just illustrated this on the top left there. If you have a slightly higher demand than supply in the grid, it's going to tend to reduce the frequency. Whereas if you have a higher supply than demand, it's going to increase the frequency. And you want to have the frequency stable at 50 hertz. That helps keep the whole grid stable. So batteries are now the largest contributor to that service. So they're keeping the frequency stable across the whole grid. And then the reason why that's increased so much is that they are better and cheaper than other technologies for doing this. So to give you an idea of how this can all fit together, this is some modelling done at ANU, and it shows you what a 100% renewable electricity supply in Australia could look like. And we're illustrating it for a challenging week. So it's in June, it's in a period where there's low solar and there's low wind, and you look at, okay, how can you make it all work and how can you make it all fit together? So we have solar generation, we have wind generation in the system, you have storage in the system from pumped hydro, you have a little bit of biomass and hydropower that's already existing in the system, and then you have the interconnection across the system, so transporting energy throughout the network. So this shows you that technically and economically you can do this if you want to. That brings me to the second myth, which is renewables take up too much land. It's easy to do a rough calculation of how much land you need for 100% renewable energy, so zero fossil fuels. And if you were using solar to do it all, you'd need around 60 square meters of solar panel per person. The fraction of land that would take is around 0.1% of the world's land, and that's at developed countries' energy consumption rates. So the overall amount of land is small. People also talk about the interaction of renewable energy and agriculture. For wind energy, of course, the turbines have to be very widely spaced just because of the way they operate, so not to create wind shadows for each other. So there's a lot of space in between, which tends to be used for agriculture at any rate. And so overall, the wind turbines provide an extra income stream for farmers. And this shows you the MacArthur wind farm in Victoria, 420 megawatts. These things are really big, so over 100-meter rotor diameter for these turbines. They're very impressive if you get up close to them. Another opportunity which is just emerging is looking at integrating photovoltaics with agriculture. There's been some work globally in this space, and there are potential benefits. For example, the regions near the edge of the panels tend to get more water, so they can give you better grass in those areas. But really, there's been not very much done here, and it's a really interesting opportunity, I think, especially for Australia, to look at how these things could fit together. And this brings me to Australia's opportunity for leadership in this space. We are installing at one of the fastest rates around the world per capita. So we're addressing all of these points, some of the first country in the world. The other point is that Australia is much more like the rest of the world than places in Europe or North America. 3/4 of people globally live in what you could call the Sunshine Belt, which is plus or minus 35 degrees. So Canberra is just on the edge. We qualify as sunshine. So it means plenty of solar and not very cold winters. And most of the growth in population and consumptions and emissions will happen in this part of the world. So Australia has a strong opportunity, and I would say obligation, to provide leadership in this area. So that's the 2 myths from me. And now I'm going to pass to Ken to talk about renewables are too expensive.
Thank you very much, Kylie, and thank you to ICEDS for the opportunity to speak today. So in order to understand how renewables compare as an energy source, we're going to have to delve into a bit of discussion around the cost of renewable energy. So to start that process, let me now talk about what is known as the learning rate for a particular technology. The learning rate is defined as the cost reduction for a unit of supply, whether that be a wind turbine or a solar panel or a nuclear power station or a television set, anything. It's the cost reduction for a unit of supply as a result of the doubling of the number of units produced, okay? So as you can see on this curve here, if you increase the number of units, initially after a product has entered the market, there is a rapid decline in the cost. So that's a steep learning rate. And as the technology matures, then the learning rate flattens out. And the learning rate is a combination of a whole series of things, mainly around research and innovation. So it's learning by doing, it's research to improve the fundamentals, it's innovation on the production line. All of these things contribute to the learning rate. And of course, if a new technology comes along with a faster learning rate, it will eventually overtake the mature technology. And at the point where those two lines cross, that is the point at which the new technology can outcompete the old. So just to give you some examples of learning rates, here's the learning rate for solar photovoltaics. So this is expressed in the same way, except we've got log scales. On the vertical axis is the cost in euros per watt of a solar panel, starting back in the 1970s and moving to the current time. And on the bottom axis, you can see the number of units of production on a log scale. So the trend is pretty much linear with a few deviations. And the interesting thing about this is that the cost is reduced by a factor of 500 over this 40-something year period. If you put that in terms of a doubling of the units production learning rate, that's a decrease in the price by 24.1% every time the number of units are doubled. And that's equivalent to a compound annual growth rate of around 33% for the last 40-something years. And wouldn't you have liked to have had a bank account that returned that capital growth rate? So that shows how rapidly renewables are reducing in price. And here's an overall comparison chart, which shows solar panels as the blue dots, onshore wind as the black diamonds. It shows batteries as the blue diamonds, and then off to the left, various types of technologies going into hydrogen production and fuel cells. And you can see that these learning rates are quite steep, they're progressive, and this is what determines which technology wins over another technology as time goes on. Okay, so the next thing we need to understand is how to compare the costs of these various energy sources. And to do this, we have an equation here. It's the only equation in the whole slideshow, as much as we love equations here at ATSI. But it's pretty simple to understand. The top of the equation is the cost of generation. Okay, that includes a whole lot of factors, including the investment cost. The maintenance cost and the fuel cost. Then on the bottom, the total amount of energy produced as a function of time t in years. And you can see there's a factor R in there. That's the discount rate to ensure that we're comparing the same prices over time. And of course, a dollar now is worth more than $1 in the future. So this is what's known as the levelized cost of electricity. In summary, it's the cost in dollars divided by the amount of energy in megawatt hours, so dollars per megawatt hour. A word of warning though, this assumes plug and play. It assumes that you, let's say, retire an old coal-fired power station and replace it with a wind farm. And of course, there may not be any wind at that location. So if that's the case, you'd have to move the wind farm somewhere else and include the extra costs of transmission, but also other things like storage, which we'll get to in a minute. Okay, so that's just a caveat. And of course, the learning rate comes into the investment cost each year, right? And as time progresses, the learning rate will drop. So if you're building a solar farm over a number of years and the learning rate means the cost is dropping over those years, you'll find that the investment cost is going down as well. Okay, so here's a calculation done by CSIRO and the Australian Energy Market Operator. It's known as the Gen Cost Study. It's done every year, and it's designed to compare the levelized cost of electricity of various generating sources. You can see on the left, the axis is in dollars per megawatt hour, where kind of $100 is a good number. And so what we see here is that the projections for solar and wind, these two bars just here, lie significantly below the cost of fossil fuel generation, particularly if you take into account the climate policy risk, which can be reflected as a carbon price, or if you remove the carbon from the generation process, it's reflected in the carbon capture and storage price. So solar and wind already are cheaper than fossil fuels. And indeed, if you take into account the fact that this isn't just plug and play, you've got to take into account the extra transmission and the extra storage. And this obviously becomes important once you get towards 60, 70, 80, 90% renewable energy. So CSIRO have calculated that here, and it shows that that even if you take that into account, the LCOE for solar and wind combined in a system goes up by no more than around half. Okay, and of course, this is all based on existing knowledge and data and understanding. If you throw into that the price achieved, for example, in the ACT government's reverse auctions held in 2020, and you work out in terms of fixed prices for that particular auction process, then the price comes in at a level that's actually somewhat less than the projected LCOE in the Gen Cost calculations. So that's a market, if you like, validation of the LCOE, which is in some sense a desktop study. But the bottom line is solar and wind are cheaper than fossil fuels and will be for the foreseeable future while we're undergoing the energy transition. Okay, so how high can renewables go? Well, as I said before, levelized cost of electricity is really just plug and play. If you get towards 100% renewable energy, what you have to then worry about is the intermittency of the solar and wind. And so to overcome that, you overbuild supply, you build more solar and wind farms than you need. You build storage, as Kylie has talked about, particularly long-term deep storage. And you need to build additional network infrastructure to connect to the renewable energy zones where all this is being built off in the regions. And in order to share the electricity generated in one part of the country with another part of the country where it's not operating. So when you do all those things and you work out the additional cost, it adds about 50% to the LCOE. This is numbers that have been produced at the ANU, but they agree perfectly with the calculations that I showed in the Gen Cost study. And if you do that, it's still cheaper than building coal-fired or gas-fired power stations. So if we look at the renewable energy pipeline, this is data from the Australian Clean Energy Regulator. This shows the investment in rooftop solar PV in green, in utility scale solar in orange, and in large scale wind in blue. And what you see is a rapid escalation in installations from around 2017. Prior to this time, the level of large-scale investment was very low. You can see that rooftop was very popular, but large-scale utility, solar and wind was very low. And principally, that was because of government policy uncertainty. Developers were unwilling to commit because of the climate wars, meaning that their future cost expectations and market expectations were uncertain, which increased their cost of finance. But nevertheless, the sheer economics of solar and wind eventually shone through, so that even with this high cost of finance, investment started to accelerate in 2017, and you can see that it's continued along at a very high level. In fact, 99% of new generation in Australia is now renewables. We've installed on average 6 gigawatt per annum of solar and wind for the last 5 years, more than 3 gigawatt per annum at utility scale, and the rest, of course, is rooftop solar, which is the highest concentration in the world. And all of this is in spite of, not because of, government policy certainty, because of the shifts in policy during this time frame. I would say that the renewable energy target is one source of government policy certainty that has remained during this time, and that has certainly helped, but the rest of it certainly did not help. So bottom line is, myth number 3, renewables are cheaper than all other form of energy, and they will remain so throughout the energy transition as we move forward. Okay, the 4th myth, renewables can't replace our energy exports. Okay, so let's go into this in a bit of detail. Let's look at our current energy trade with the world. These are figures from the Department of Climate Change, Energy and Water. And what we see here is the dominance of fossil fuels in our export structure. We export lots of coal. This is numbers in petajoules. We export lots of natural gas, bit of crude oil and other products. We import quite a lot of petroleum products as well, and even a bit of natural gas, which is mind-boggling given the amount we export. But nonetheless, this is what happens when you have a distorted market system. And you can add to that our exports in uranium, which, although this graphic somehow has been lost in translation on a PC, we export nearly 5,000 tonnes of uranium per annum, and that's around about 3,000 petajoules of energy. And it's not included in these statistics for some arcane argument around the fact that we don't have nuclear power in Australia. Okay, so that's our energy export profile at the moment. If you look at our top commodity exports in 21, this shows their value in dollars. You can see that iron ore is the biggest, coal follows shortly, followed by liquid natural gas, and then alumina. And a question to keep the live audience awake here at ICEDS headquarters: what sits between LNG and alumina as an export value earner? No. Higher education. Speaking as someone from the university sector, I had to say that, didn't I? So this indicates our reliance on the export, not only of fossil fuels like coal and LNG, but also of iron ore and alumina, which require fossil fuels in one form or another to transform them into metals. Okay, so let's look at the work that we've been doing in the ANU Grand Challenge Zero Carbon Energy for the Pacific on this export future of Australia, which has to be transformed from one based on fossil fuels to one based on renewable energy. Otherwise, our economy is going to go completely down the gurgler. So this project at ANU was a $10 million grant from ANU, funded over 5 years. We had 5 programs on hydrogen fuels, renewable electricity systems, green metals, policy and governance and on Indigenous matters. And we produced this paper early in the piece, which looks at the potential for renewable energy exports in terms of replacing our current export composition. And so if we evaluate what we export now in terms of the amount of CO2 it produces, not just in Australia, but overseas. So this shows the amount of exported effective CO2 resulting from either the burning of the fossil fuels or from the processing of the ores, the iron ore into iron and steel, the alumina into aluminium. And this all happens, of course, in our major trading partners, which are located in the Asia Pacific. 98% of the greenhouse gas emissions arising from this occur in the Asia Pacific region, and that contributes 8.6% of the total emissions of the Asia Pacific. So we are a significant contributor, if you like, in that sense to the Asia Pacific's emissions. If you put this on a graph which compares it with our domestic emissions of just over 500 megatons of CO2 equivalent a year, you can see that our exports amount to around 3.7 times the domestic emissions. So this is a really significant number and a major contributor, of course, to the Asia Pacific's emission profile. So all of this is going to change as the Asia Pacific and the rest of the world decarbonizes. These markets will gradually disappear and go away. They won't go away in terms of the ores, but they will in terms of their processing modalities. And of course, Australia is well positioned to shift from this fossil fuel export economy to one which relies on our excellent renewable resource. This shows the solar resource in Australia. It's a snapshot of the picture Kylie showed before. And what you can see is that in certain parts of Australia, our solar resource is double what it is in some northern latitude industrialised countries. So they will look to Australia for energy supply because either they don't have the resource there or they don't have the land to produce it. So let's look at a future Australian export scenario. And for some reason, we've lost the map. Why is that? Anyway, let me do it in words. Okay. If Australia, we'll base this on two business as usual assumptions. Okay. Australia continues to export the same amount of energy in petajoules as we do now, except it'll be renewables, not in fossil fuels. And the second business as usual assumption is we continue to dig up the same amount of ore as we do at the moment, but we don't export that as ore. We export it as processed iron and steel or processed aluminium. Okay, so the first assumption, export the same amount of energy as we do now. Let's say 80% of that is hydrogen. That means 65 megatons a year. We also assume that 20% of that goes as renewable electricity exported through high voltage direct current undersea cables to Southeast Asia and beyond. And that would amount to 540 terawatt hours a year. Okay, I'll put this all into context in a minute as to what those numbers mean. So those are the assumptions. We didn't assume any more electricity export because you can only have so many cables going under the ocean. Okay, so second assumption, mine the same amount of ore, but you export green steel, 510 megatons a year compared to 6 megatons a year now. Okay, that's a huge increase. And 18 megatons of green aluminium compared to 2 megatons now. If you add up the amount of energy, renewable energy you need to do that, that comes to 7,040 terawatt hours a year, which sounds like a big number, and it is. It's actually 27 times Australia's present electricity generation. Okay, so that's enormous. Add to that the fact that we've got to go from a fossil fuel-based domestic economy to one that has 3 times the amount of electricity use because we're electrifying all the industrial systems and our electric vehicles and all the rest of it. That requires another 3 times. So you've got basically 3,000% renewables in our future electricity sector. Okay, so that's 30 times the amount of electricity we produce now, and it's all renewable. Okay, so that's an eye-wateringly big number. You might not believe it, but let's say only 10% of that is true. Okay, that still means we need to double Australia's zero emissions electricity future because exports will be 3 times and domestic will be 3 times. So we're going to talk about a 600% renewable energy future, at least. And just to show that we're not, and just one final point on this, there's a key message here that on and off-grid renewables for export may well dominate and influence the price and supply in the domestic electricity sector, okay? Because of this massive export opportunity, which we need, because otherwise we won't pay our way in the world. So this means that this is going to be a significant factor when it comes to planning our future electricity system. Okay, so just to show that we're not alone in seeing this future, this is the same picture Kylie showed, but with another scenario produced by AEMO in the integrated system plan. It's the green energy export future scenario. And what it shows, and this is only for the national electricity market, which is the skinny grid on the eastern coast, okay? It shows that there will predicted to be a doubling of the capacity needed on the east coast. Remember, most of this will happen off-grid probably, and it won't happen anywhere near the NEM on the east coast. So this is just showing that even under these limited circumstances, our baseline scenario is not only likely, but it's going to be exceeded. So we are not alone in predicting these numbers. Let's have a quick look then at what this might look like in terms of the export industry. Here's the current export projects for renewables, mostly hydrogen. And if you add them all up, they exceed 120 gigawatts of capacity, bearing in mind that the total electricity generating capacity in Australia is at around 65 gigawatts, okay? So this is the ones that are talked about at the moment only, okay? Let alone the masses of projects that will happen in the future. There's the Asian Renewable Energy Hub up in the top there, which is looking to export hydrogen and ammonia overseas and maybe produce some electrons for the mining operations in the Pilbara. There is the Yarra Pilbara project. The Yarra Pilbara is the biggest ammonia exporter in the world. They aim to shift completely to renewables and export ammonia to the rest of the global supply system. There's Murchison Renewable, Infinite Green Energy, Western Green Energy. There is the Western Green Energy Hub, which is a 50 gigawatt project projected for the Great Australian Bight. That's even bigger than the Australian Renewable Energy Hub at 26 gigawatts. So that's a massive project. And then there are a number of projects in Adelaide and a bunch clustered up around Gladstone in Queensland. And then, of course, there is Sun Cable, which aims to export electricity through a high voltage DC undersea cable through to Singapore to satisfy 15% of Singapore's energy needs. Okay, so one final slide just to talk about green steel. So this is a real export opportunity for Australia. You might not believe in the hydrogen economy. You might think that, Sun Cable is a pie in the sky project. But green steel has, I think, real possibilities, and this could dominate the amount of renewable energy we generate for exports. And the reason is that blast furnaces, of course, use coal. That's going to disappear. It'll be replaced by an alternative process to remove the oxygen from the iron oxide in the ore. Okay, so it's called reduction, reducing the iron oxide. And this will be achieved once we have supplies of hydrogen, which will be the reducing agent instead of carbon, and renewable energy will provide the heat for this process. And the sweet spot in the entire steel production process will then be this point here, HBI, hot briquetted iron, which is produced by this direct reduction iron process. And that is the sweet spot for the Australian export industry because it's easy to export. It means that we don't need to have the high value add steel making capabilities at the end, which are often best located next to other manufacturing processes. The rest of the world will love us because that will mean going into their electric arc furnaces, they have a cheap supply of hot briquetted iron, and they will get the value add into these high value steel specialized processes that their other industries need. So that's a real prospect for renewable energy exports, but it's embedded renewable energy, and the same is true of aluminium exports. Okay, so that's pretty much the end of the presentation. We've gone through 4 myths. The first one, that renewables can't be relied on to meet demand and keep the grid stable. Will Kylie show that that's not true and that indeed this is possible? Renewables take up too much land. Well, no, they don't. Indeed, you can do other things on the land at the same time. Renewables are too expensive. No, they're not. They are, in fact, the cheapest form of producing energy and will remain so. And finally, that renewables can't replace our energy exports. Well, not only do we have to replace our energy exports, but renewables are really the only way and probably the best way to do that, either in direct form or an embedded form in hydrogen and metal exports. So there we are. We're now at the end of the presentation and we've got a quarter of an hour or so for questions. So thank you all very much for your attention.
Okay, thanks everyone. Thanks for the wonderful presentations. I think we might take a few questions from the audience online first, and then any questions from people here in the room with us today. The first question I think is probably for both of you, and it's around population growth. Essentially, how are we going to offset the increase in the world's population and consider that in relation to the energy demand it's going to create?
Can I start? So very recently I was in India and I picked up a copy of the Times of India, and there was an interesting article in there about India's population. And what the article showed was that the replacement rate for populations is around 2.1 people for every couple, 2.1 children for every couple. And if you look at the demographics of the world, what you find is that the world's demographics have changed. So we now have around 8 billion people. This will peak somewhere around 10 billion, maybe closer to 11. And then this will progressively drop off next century, probably, to end up at around 2 or 3 billion people. So what we've got to do is survive the next 100 years. And demographics are inexorable. You cannot change them. You have a certain population of young people who are going to have children, and their, birth rates are what we know at the moment. So the birth rate in Australia is below replacement. It's below 2.1. It's, 1.7 or something like that. In Asia, it's often as low as 1.5. In India, guess what? It's 1.8, right? So India will not replace its population in the future, right? Even though it's grown to a high level now, that will gradually turn over. And a lot of other countries are very similar, Africa being the exception. So this is inexorable. The world population will decline eventually. We just got to get through the next 100 years.
Yeah, just to add to that, of course, these projections that we've been talking about are taking into account the increases in population and as well as the increases in energy consumptions in developing countries, who, of course, will want to get up to our living standard. So all of these projections that we're talking about, that we can get to the demand required, take into account the increases in population and increases in energy consumption.
Thank you. This one's for you, Kylie, I think, on myth number 2. What kind of demand is that 60 square meters of land per person based on? Developed or developing society?
So that's assuming that everyone is consuming at developed country rates.
Another question from John McGar. And this is for you, Ken, what is the assumption regarding hydrogen exports? Is this liquefied hydrogen? Do you take into account energy loss in liquefaction?
The numbers that I showed you are purely for the supply at the factory gate. In other words, in Australia, they don't talk about how you get it from there to the customer gate in another country. It's not an economic projection. It's purely a series of numbers to show particular scenarios for export. So you're right, there is a question around how do you get it from Australia to the customer overseas. There are a number of opportunities. One, as you mentioned, is liquefied hydrogen to get it down to incredibly low temperatures, which is very energy intensive. The second is to use other materials like liquid organic hydrogen carriers to grab the hydrogen and you ship it in this material, and then you release it at the port of supply. And then you can also, do compressed hydrogen, but that's very inefficient and it requires large volumes and that sort of thing. So the answer to your question in terms of how do you do this is not clear yet. And indeed, it may be better, as many people and countries are realising, to generate the hydrogen on site and use it on site, or you convert it into something like ammonia, or you use it in an industrial process like green steel or green iron in Australia's case. Export of ammonia is tried and tested around the world. It's a huge industry already. We know how to do it. That might be one way of transporting the hydrogen as well, but you would probably then use the ammonia for fertiliser production or other things rather than turn it back into hydrogen again.
Terrific, thanks. I've got a few more questions from the online audience, but are there any questions from folks in the room?
Thank you. Kylie, in relation to myth number 2, indeed, the total amount of land required is tiny. As you pointed out, it's 0.1%. The bigger area of discussion appears to be which types of land are used. Are they close to grids, close to cities?
Mm-hmm.
Or do they happen to be high value land for other purposes, including agriculture, but not limited? Would you like to elaborate a bit more on that location dimension?
Yep, for sure. So I guess there's a few things related to location. Wind is quite specific in where it needs to be located, and this is because the power from wind goes up as the cube of the wind speed. So it's very sensitive to wind speed, so you have to have a very good location for wind. Because of that, it also does tend to be on ridge lines and things like that, where you have a good wind resource, which often doesn't compete with agricultural uses. But of course, you need to think about the environmental impacts, and that definitely has to be a part of the assessment. For solar, you can put it in a really wide range of places when it comes to resources, because the solar resource doesn't change a lot in many parts of Australia. If you're looking at the East Coast, you can put solar in very many places. So the thing then you need to think about is where you put it relative to the grid. So that needs to be taken into account, that trade-off across agricultural land uses. But again, you also need to think about, can we have a dual use of this land? And this is an opportunity that we need to think about further.
And can I just add to the land question? So unfortunately, the graphic didn't show up, but the map that I had of Australia with the export scenario showed a little square which represented the amount of land you would need for that scenario. Remember, it was 27 times the size of our current electricity generation system. The size of that square is about 170,000 square kilometres, or around about just over 2% of the land area in Australia, which is a little bit more than we devote to forestry at the moment, and it's only about 4% of the land used for grazing, okay? So that shows that it's a doable amount. It's huge, it's eye-wateringly big, but nonetheless, it's doable, and that's for 27 times the amount of electricity we produce at the moment, okay? So this is all possible, and remember, as Kylie said, this land can be used for other things. If it's used for pastoral purposes, you've covered a small fraction of that 170,000 square kilometres in turbines and solar cells. Most of the rest of it, the vast majority of the rest of it, is still available for grazing.
Yeah, question here.
Ken, you haven't mentioned offshore wind.
Good question. Right.
It's not a question, it's
I know, that's right. So in the GenCost study, there was a small bar there for offshore wind. So they've done the desktop calculation of how much that might cost. It comes in more expensive than onshore wind. And so, you would expect that companies would most likely develop onshore wind before they develop offshore wind. But remember, the levelized cost of electricity is plug and play, okay? So one of the incentives why you might want to introduce offshore wind is because you have a place onshore nearby that you can just plug straight into the grid. And that's true in the Latrobe Valley in Victoria, where all the old power stations are retired, but there's a perfect grid connection for offshore wind just offshore from that location. So it might make sense to have offshore wind, which is more expensive, located there, and then simply plug straight into the grid at that point. Other locations that are being looked at, particularly around the Illawarra and around the Hunter region, also have that advantage. They've got big connection points nearby on shore. And so that's why they're being considered, and less so in other parts of the country. But by and large, it's more expensive. It's also starting to create a little bit of opposition from people that don't like to see wind turbines when they go to the beach, which is understandable. But if you look at floating offshore wind as opposed to fixed offshore wind, which is actually located on the seabed, you could put those turbines further out to sea where they won't be visible. And that technology is starting to improve. The costs are coming down in places like Europe. Countries in Asia are looking at flexible floating offshore wind. So that might change the equation as well.
Yep, question.
Thank you, Ken. Thank you, Kylie, for the interesting presentations. My name's Scott White. I work for the EU delegation around the corner, the European Union's diplomatic mission. Just a 30-second plug. We actually have coming out to Australia the EU's Energy Commissioner at the beginning of April. So she will be discussing, no doubt, many of the points that you've raised with her counterparts, Ministers Bowen and King, during that visit. I had a quick question, and that was in regards to rooftop PV, and you've highlighted the AEMO and other analyses showing the high levels of current deployment and the potential going forward. So even though there are already very high levels in terms of, say, residential rooftop PV, there's capacity to dramatically increase that, of course, but that's not without its problems in terms of load dropping right down, etc., as you well know. So I'm just wondering what your views were, how optimistic you are about there being potential solutions to those problems. And I'm not saying rooftops have solved it as a problem. It's not. It's part of the solution. But as I say, there are still these issues that one can't ignore. So I'm just wondering what your thoughts were on that, please. Thank you.
Yeah, I'll start out.
Either of you.
Yeah. Well, firstly, I'd like to acknowledge the leadership of the EU in all those drop downs in price. So Ken talked about the reductions in price, and that was largely because of countries like Denmark and Germany investing and getting that installation out there and reducing the price. In terms of rooftop solar and how it can fit within the distributed energy system, so you saw in the electricity market operator plan, there was a lot of rooftop and also a lot of consumer energy resources that were coordinated. I think those two very much go together, so that if you are going to have that increase in rooftop solar, you also need to have the home batteries and potentially also electric vehicles coordinated, so that that's all working together at the distribution system level, so that you can have everything working out at the distribution system level without having to export to the transmission system, for example. So I see that all fitting together very well. So rooftop installation is going fast, and what we need to progress especially is the batteries and electric vehicle integration, and have those in a coordinated manner, and also have those in a way that works for both the network operators and the consumer. So this is something that hasn't quite been worked out yet. It has to be clearly something that the consumers want and will sign up for, but it also has to be something that the network operator, they can be sure that it will help keep the system stable.
And maybe I could just add to that, there's a clear role for government in this. So as Kylie pointed out, if you do things properly at the local level, you reduce the need for major upgrades in the transmission network. If you're a consumer or a distribution company, why do you care, right? So somebody has to care for the whole system, and there's a clear role in government for making these things happen and reducing the cost for everyone. So that you can socialise, if you like, the cost of having, shared batteries in a local area, et cetera, which reduces everyone's transmission costs, which would otherwise have to increase under this, 2 or 3 times electrification scenario. So clearly, there's a role for government here.
Great. Just going to some more questions online. One for you, Ken. On the green steel flow chart, which you showed with carbon monoxide, how is this made with renewables?
Yes, so you can just inject a bit in there for the steel process, but you don't need it for the iron process. And that's why I'm saying that it's the iron production process that Australia should be focusing on and leave the steel production side to everybody else.
Great. And another question, has there been an estimate of the energy and environmental costs of mining, processing and recycling of all the materials needed for renewable infrastructure?
Well, this goes into life cycle analysis of everything, really. And indeed, you look at life cycle analysis. I know of a wind turbine, let's say, it pays its embedded energy costs off, within a very short fraction of its entire lifetime. That's true of most things. So you have to take into account embedded energy costs and embedded carbon costs when that energy is not produced by renewables. but by and large, these costs are a relatively small component of the total product.
Just like to add to that about recycling of solar is that a lot of the materials in these systems are commonly recycled materials. At any rate, if you look at the weight of solar panels, it's mostly glass and aluminium framing. So there's standard processes for recycling those. At any rate, so certainly it needs to be considered, but a lot of it is something that we do anyway.
Great. Another question which has popular discussion at the moment. Nuclear energy appears only briefly in the analysis. It's so costly and dangerous. Why is it that other countries seem to be embracing this technology at an increasing pace?
How long have you got? So in a few seconds, other countries have embraced nuclear energy before and they're continuing to make use of it and they're extending the lifetime because it's cheap to do so. Are they building a lot of nuclear now? No, they're not. Some countries are starting to ramp that up again. The IEA predicts that nuclear will continue to be a component of the future energy system because not every country has the land or the renewable resource to do what they need. In Australia, we've got plenty of land, we've got plenty of renewable resource. The only time you would even get close to thinking about nuclear is the last couple of % of decarbonising the electricity system, when the cost of overbuilding renewables and all the other factors, storage, etc., become very high as well. And then it might start to get cost competitive. But by then, we'll be so far down the track that, it would take forever to introduce a regulatory system and all the rest of it for nuclear and it would just take too long.
Yeah, so, yeah, I agree with that point. It'd be too far down the track. We'll be installing at much greater rate. And I showed in one of my early graphs just how much more solar photovoltaics than we are installing than nuclear. Nuclear was one of the small technologies on the right-hand side. And indeed, we started installing more solar than nuclear globally about 20 years ago. So that's when solar passed the annual nuclear installations.
A few more questions online. What are the opportunities and constraints of building a green LNG export industry using green H2 and CO2 to produce? It would build on a large existing capacity and well-tested technology in this space.
Well, if there's no market for LNG, why would you do it? I mean, there will be no market. This is the world is going to change, right? Processes in industry will change. People will be hitting their houses with heat pumps. There will be no market. So why do it?
Also, it would be unbelievably expensive. Using carbon dioxide to put things together it's a very expensive and energy intensive thing to do.
Very good. So next question is just responding to your points, Kylie, around EV integration into home PV systems. Currently, there's no two-way charging possible except in South Australia for a couple of models. What needs to be done to push that forward fast?
I guess there's a lot of things that need to be done to enable two-way charging, and one of the things is just to have the models that make it cost effective. So there's been studies recently and it just doesn't work economically. So I would say that that's something that we need to start working on, but there's a number of other things that I would do first with electric vehicles in terms of getting more charging stations out there, all of these kinds of things, making sure that the charging is controlled. So the two-way part is important, but a little bit further down the track.
More questions, folks in the room? Ready?
Thinking of structural barriers to the realisation of your scenario, one that I could think of is the availability of STEM skills professionals in Australia and globally. What other structural barriers do you both foresee, and how are you accounting for them?
Deep question. So not a structure, well, depends how you view structures. Social license is a big issue. And we have a lot of people working in the social and human sciences in these areas. We've seen that one of the roadblocks for renewable energy zones is not being able to connect through transmission lines to the load centres in the cities. And this is driven in part because negotiations with landowners haven't gone, down the most appropriate paths, and they haven't taken into account the needs of communities and all these things. So it's a very complex area and one that needs more research. But by and large, there needs to be a well-informed, gold standard approach to negotiation with landowners when it comes to installing these massive new developments, whether it's solar and wind farms, whether it's transmission lines or whatever. And I think that's a really important area of research, really important area of policy, and a really important area because you've got to bring everyone along and show not only that it's going to be worth their while economically to have these infrastructure projects on their land, but also that it's going to reward them in some meaningful way to supplement their income, whether it's be from farm income or whatever else, and provide some stability.
Just to add to that, so I talked more about solar in my talk, but wind is also an important part of the mix. And wind globally is not growing as fast as it needs to make the contribution that it needs to. And the major factors are there, the social license, that's one of it, but also the approvals process. And the approvals process are quite difficult now because of the lack of information that's available. So a developer has to propose to put a system in a particular situation, and then the market operator will say whether they can do it. They'll approve it or not, but the developer doesn't have all the information about whether that's an appropriate site in terms of the grid connection. So because of that, there's a lot of time that's spent in actually making all these proposals, and it's difficult because all this is commercially sensitive information, but it seems that there should be a better process for making information available to everyone that can expedite all this.
Terrific. We've just had one more question come in. Australia exports far more coal than we consume domestically. How can we wean our economy off this historically lucrative business, digging stuff up and selling it?
Well, there's kind of two answers to that. One is the market's going to dry up anyway, so we've got to. And the second is we can just lay over the top of what we're doing now a completely new industry based on renewable energy exports, whether direct or embedded. So, in order to export, I don't know, ammonia, which is an energy vector and also a product that can be used elsewhere, you don't need to close a coal mine. You can just do it by building a solar and wind farm, set up a hydrogen electrolyzer system, and a harbour wash process for producing the ammonia, and then just export the ammonia. It doesn't depend on the shift in what's happening to our fossil fuel economy at all. You can do it right now, and that's part of the beauty of it, that you can create an entire new export industry to replace what we do now without having to even think about what happens to the existing fossil fuel exports.
The other thing is that there will be increased demand for a range of minerals because of the renewable energy transition. So we can keep digging stuff up and selling it.
Different stuff.
I have a question if
It's not a question, but I'm going to throw in a wild card. And that's the issue of geological hydrogen.
Mm-hmm.
It's suddenly become really very, for those who don't know, people have started looking at geological hydrogen and you can find it.
Mm.
The issue is how much can you find?
Right.
And the US, I think it's either USGS or the US Department of Energy, had just come out the paper in the last few days in which they've said there's enough geological hydrogen to meet all the world's energy needs. Now, I think it's a bit of a tall order, but anyway, that's what they're saying. And so, have you factored in, a wild card like that?
Yeah, it's a very good point. And in fact, Geoscience Australia are doing a similar survey and are mapping the potential geological hydrogen reserves in Australia. And they're usually in gas wells, in underground repositories where there's an impermeable layer above. So yes, it's important. Whether you can extract it at a cheaper price than you can by doing electrolysis of water is another question. But yeah, absolutely, we should consider it.
So yeah, my question is more around economic policy, and seemed like a good opportunity while you're both in the room. But last week was an interesting week. Ross Garnaut and Rob Sims addressed the press club and called for a carbon solutions levy. And you were talking about policy certainty before. Do you think the introduction of a new-ish concept, building on what's been done in the past, could help mitigate greenhouse gas emissions and carbon? I guess what's your views on it as a viable policy option in Australia at this juncture?
Well, I guess the other thing they said at that press conference is no one's going to do it because it's too much of a political hot potato. So that's worth considering. So for a very long time, as long as I can remember, economists have been united in their agreement that a carbon price is the cheapest way to transact the energy transition and indeed to transact the entire transition to net zero. That hasn't changed, right? The only thing that's changed is the sensitivity of politicians to focus groups in marginal electorates that tell them that might increase their bills and they don't want it, right? So it's not that it's not a good idea, it's just that politicians party machines are telling them that they're going to lose votes in places they don't want to lose them if they increase the price of things through a carbon tax. What they don't understand is that when you've got that money, you can shift it somewhere else and either compensate all those people who are bleating at you, or you can do good things with it, like fund the network infrastructure or whatever it is that's needed for the energy transition. Same concept with the Garnaut and Sims proposal, except that you don't have a uniform price across the whole economy, which economists argue is the most efficient way of doing it. What you do is you tax the fossil fuel production at source, and then you do the same thing. You take that money and use it to do good things, compensate people and provide the necessary investment going forward. It's a variant on an old theme, but in a way that hopefully might be more palatable, but even they recognise that in Australia, at least, we are gutless about this and won't go near it.
And I guess the broader point is policy certainty, which is certainly the thing that we need. And the more that we have, the more that we can invest. You can see in the US, they have the Inflation Reduction Act, which has led to an enormous increase in investment there. We've seen that this is a huge opportunity for Australia. And so we need the right policy settings over a long time that allow us to take advantage of that opportunity.
John.
Thank you. May I just take an opportunity to connect three things? We talked of policy certainty, we talked of social license, and earlier you mentioned multiple benefits or multiple use at one moment. It occurs to me that a great proportion of our current policy and public debate tends to treat energy just as energy policy without connection to anything else around us. So it's in a silo. And that creates a significant degree of social license issues. And I wonder if there's been much work, or would there be any value in thinking about work that looks at the cross-sectoral benefits. Let me just take two examples. Is there any potential in thinking about issues of mitigating or adapting and reducing to coastal erosion because of offshore wind? It's just an idea that came to my head now. Secondly, in relation to panels, I've been aware for quite a while in Asia, but specifically in southern India, about the use of elevated solar panels for the production of temperature-sensitive vegetables, which is both great income for a lot of people because of the demand for those particular types of vegetables in the urban areas in India, basically European temperate vegetables. And so it's just another example of where there's an economic case of linking, in this case, vegetable production and elevated panels. So I just wonder, is more generally, are there linkages that we're missing or that it might be worth researching in order to broaden the debate away from just purely energy?
Yeah, that's a good point, John. And it's interesting to think of how things are linked. There are certainly links between energy and water demand, for example, and that some of these energy systems will require less water than existing fossil fuel systems. I mentioned that the agri-photovoltaics before, so the combining solar with agriculture, and indeed most of the work that's been done so far is with crops, and it is does look like it has potential. Yeah, there's been little research done in Australian conditions, so I think that's a big opportunity.
Yeah, and I think your idea that, you know, we should join the dots across the entire economy, looking at all sectors, is an important one. So we have at the moment sectoral plans being produced by the government in 6 areas. Energy is one of them, but as you say, energy informs a range of other areas. It informs industry, agriculture, transport, you name it. So, you know, from an ICEDS perspective, people that do systems integration or take a systems level approach to problems usually find more success than by carving up the problem into little bits and solving all the little bits. So that's true of the approach in a policy sense to this issue of how we're going to decarbonise at the lowest cost at the fastest rate. And so an holistic overview of energy use across the entire economy, remembering that the integrated system plan only deals with electricity in the national electricity market on the East Coast. It doesn't deal with electricity anywhere else. It doesn't deal with gas. It doesn't deal with space heating. It doesn't deal with transport fuels. It doesn't deal with the vast majority of the energy use outside the NEM, which happens everywhere else in the country. So a joined up approach to a holistic solution for energy systems is important. I'll give you one example of why it's important. So as part of the hydrogen research delegation to Germany a year or two ago, I visited a large steel production facility in the Ruhr Valley. That is part of an ecosystem in the Ruhr Valley that not only shares infrastructure like electricity, it also shares process heat, waste heat. The flue gases from the blast furnaces go to the chemical industry next door. This is an ecosystem. It is not a single factory with another single separate factory next door. All that's going to change, right? The blast furnaces are going to go away. There will be different types of manufacturing. This will change completely. So the ecosystem is going to change. So unless you have a joined up dots approach to the decarbonisation process in this type of complex integrated industrial system, you're going to get a less than optimal result in the end. So this is why we need to take an holistic view, and that's why a systems approach to the energy transition is incredibly important, not just at an engineering level, not just at a planning level, but at a policy level.
Well, that's a wonderful moment to end this discussion on debunking misinformation on myths in relation to renewables in Australia and beyond. Well, I'd like to leave us with that note of systems approaches that are needed, and we'd like to extend a huge vote of thanks to Kylie, Professor Kylie Catchpole, and to Ken Professor Ken Baldwin, for these excellent presentations. It's been very thoughtful, very important discussion that we've had. I'd like to also extend a thanks to all the participants, both online and here within the ATSI office, for your questions, for your participation in this process. We would very much hope that this conversation can continue beyond this webinar. Please keep in mind that this has been recorded and that this will be put up onto the YouTube channel of ATSI and is available therefore for reviewing or also for sharing with your colleagues. Please do feel that you can pass this on to your colleagues in order to expand this conversation about debunking myths that are holding us back in terms of making better use of the technology. A final comment from ATSI, we would like to thank very much also the co-sponsorship from the Institute for Climate, Energy and Disaster Solutions at the Australian National University, which is a very active group in this space within Australia and internationally. So thanks very much to everybody for contributions all round, and let's keep this conversation moving ahead. Thank you.